All right, number 16 is my first request. I will go over anything you guys want to see, absolutely anything. But 16, like I said, was the first one I've had a question about. Beautiful. This is a lot like number 1. Very, very similar to number 1. Your parents bought a football helmet signed by Drew Brees in 1999 for $110. The value has been increasing 3.02% each year. We're going to round our answers to the nearest penny if necessary because we are talking about money. All right, I'm going to start filling in the table because we know the value in 1999. That'd be 110. So I'm going to go ahead and fill that piece in. Writing a function rule for this situation. You guys have a whole bunch of formulas up at the top at the very beginning, like in that box. I will make sure that you have access to all of those formulas, but all of them basically boil down to this. The other variations of it are just to kind of help remind you of, like, did you remember to take these ideas into account? But all of them boil down to this idea here. So I know I'm going to need to start with a y equals. I know I need my initial amount, which would be what? 110. And then I'm going to need some parentheses. This is where our value for b is going to go. They gave us a percentage, and they said it's increasing by that amount. When they first bought it, it was worth what percentage of itself? 100%. And as time goes by, it keeps increasing by 3.02% each year, which would give us a growth value of what? 103.02%. I can't put it like that inside my parentheses. So what do I need to do to it? Move the decimal 2 places, which is the same thing as dividing by 100%. 103.02%. We're going to divide that by 100%. So my percents cancel. That's how I know this is not going to be a percentage. Yes. Now, I will caution you guys. Most of the time, I tell you we can just round to 2 or 3 decimal places. When we're finding a value to put in for b and when we're using exponential functions, if it is a terminating decimal, like this one, it stopped, it didn't keep going on your calculator screen, even though it's not 4 places, use them all. On exponential functions, it will make a large difference in your final answer if you do not include all those pieces. So 1.0302 to the power of t. That's what I would use as my rule. It says use your model, and by model they mean the function rule. To predict the value in 2005. When was this helmet bought? 1999. So 2005, how many years have passed? 6 years. So 6 years later. I'm not going to put 2005 in for time, because if I do that, I'm saying it has been 2005 years since it was purchased. Time is not looking for the year it is, like by the calendar date. It's asking how much time since you acquired this thing or since it began. So I would put 6 in the place of t. So into my calculators. Let me make some room here. Y equals 110 times 1.0302 to the power of 6. And this is how we're going to get this answer. If you guys wouldn't mind grabbing your calculators and popping that in. Remember, we're going to round it to the nearest penny since we're talking about money here. So I need 2 places after the decimal. I know it's going to be worth at least $100 because it didn't go down in value, right? You said, I'm sorry, what were the two digits after the first one? 131, you said, and 49 cents? Beautiful. If you rounded that to 50 cents, that would be fine. Yeah, I'm fine with it. If you're off by a penny or two from my answer, but I look at your process and I'm like, there's no way you could just fumble your way into this answer, we're golden. Nobody's going to throw down over a couple of pennies. What is it worth this year? Okay, so I'm going to put the 131.49 here. There we go. What is it worth this year? Well, this year is 1999. Or sorry, 2022. I looked at the wrong spot on the table and then my mouth started moving. 23 years later. This year, 23 years later. My son was born in 1999.
So he's 20.
He'll be turning 23 this year, yeah.
Wow.
It hasn't been his birthday yet, but he will be. I do not feel ready to have a 23-year-old.
Oh my goodness. Does he live here?
He lives up in Chicago. To the power of 23. What do we get for its value this year? $218.06. Again, 5 cents, 6 cents, 7 cents, anywhere in there, I'm going to be okay with that. All right. So far, so good? Mm-hmm. All right. We need to graph this. However, you just found 3 points that belong on this graph, didn't you? Mm-hmm. All right, so all we're going to need to do is decide on the scale on the graph and plot those points and trace through it. What should we count by on the y-axis? Should we count by ones? No.
Probably like 3. 3s are 2.
On the y-axis?
On the Y?
Yeah, I'm thinking up and down.
Isn't that years? No. Why? Oh.
Yeah, like can't you do like 1999, like 2000?
That'd be my x-axis. We can do that one first. Okay, you said you wanted to count by 5s on the x-axis?
Oh, the Y is supposed to be what then?
The y is what values? Let's look down on our table here.
Oh, see, I'm thinking the X's.
Yeah, our x's are the years.
Oh, okay.
Your input, what you're putting in the place of the variable, that's going to be what goes on your x-axis because that's your independent variable. The y-axis is your output, which in this case is money. What do you guys want to count by? 10s?
Because you're skipping from 1999 to 2005 by 10. That don't really fit.
Okay.
I would say 5.
5s, and that's for the x-axis or the y-axis?
The X.
The x-axis, okay. So I'm going to start 1999 is here. I'm not going to put 0 there because they didn't buy it in year 0. They bought it in 1999. And then let's see. 5, 10, 15, 20, 25. So 5 years after 1999, that would be 2004. And then 2009, 2014, 2019, and 2024. So we're going to have to kind of ballpark where 2005 and 2022 are, but I'm not super worried about that. What should I have on my y-axis? Count by ones? No. Count by hundreds? By 50s? Okay, we can count by 50s. Let's see. I need them closer together than that. 50, 100, 150, 200. That would put 250 up here. All right. It started off being worth $110, so right about here. And since we're going to have to do some, like, we don't have the grid in the background, we're kind of approximating the location of these points. When in doubt, make your dot bigger. As long as your dot captures where that is, because we want approximate locations for these things. $131 is going to be about where? In between the 100 and the 150, but above that dark blue dot that I have there, right? Okay, so I'm thinking it's like here-ish, and 2005 is going to be after 2004. So those two cross right about here. So far, so good? Nice big dots so that I make sure I got it. And then $218. It's going to be up here. 2022 is going to be right about here. So get my big dot in the background there. All right. Are we good so far with how I've gotten these points? All right. If you hold a ruler up to those dots, does it make a straight line? No. It is curved. It's just not super curved, but it is very slightly curved. So then you're going to grab your pencil. You're going to trace through those points, and it's continuing up this way. Is this an example of growth or decay? Growth. It's increasing over time. The value of the helmet is increasing over time. Did that answer your questions? Awesome. What else would you guys like to talk about, look at, see, demonstrate? 15 and 17. Cool. So on either side of this one. First one I heard was 15, and then we'll go do 17. 17 is a great one. 15 is 2. Where do I look in this equation for the starting amount? Before the parentheses, this right here. This is our initial amount. All right, so 5575. Is this showing growth or decay? Decay. How do we know? Yeah, right here. The B value, which is 0.65, is less than 1. All right, so we want to write that rate as a percent. I'm not asking about the starting amount here at all, so I'm only looking at that 0.65. I need to write that as a percent. How do I do that? Times it by 100%. 65%. This is telling me the amount that is remaining. This is not my rate. We have to subtract 100 from it to find the rate. So I'm going to subtract 100% from this. What does that give me? Negative 35%. And I just realized that up above I forgot to actually write decay. This is showing decay. All right. So the negative part of this I'm not going to put on the line. Negative only tells me it is decay. So that verifies what we answered up above. I'm only going to write the 35% on that line. Because we're going to go write a story with this, and when they write a story, they're never going to say it's negative 35%. They would say it's decreasing or declining or going down by, or people are leaving at this rate. So that's why we're only putting the whole number percentage without any negatives with it. All right, so we want to write a story that could model this equation. My story needs three things. It needs to have a reason for the starting amount. So I need to decide that it's 5,575 of something. It needs to include that it is decay. So I need some signal word in there to show me that it's going down over time. And it needs to have the rate, 35%. It does not need to be a long, complicated story. You could do it in one sentence.
What's that R word?
Rate. Sorry, it's kind of sloppy. There. All right. So 5,575 what? People. Okay. My neighborhood currently has 5,575 people. Each year, what happens?
It started decrease.
Yep. Each year, the population decreases. Yep. By 35%. Done. I took 2 sentences to do this, but there are ways that you could write it just one sentence. I need the starting amount, and you need to give a meaning to it. Dollars, people, peaches, kittens, I don't care. You need to include whether it's increasing or decreasing, some kind of signal word, growing, decaying, increase, decrease, earning, losing, and then I need the percentage. That's all I'm looking for on the story. Number 17 was the next one that I heard called out right after 16. So we did 16, 15, and now we'll go do 17.
Wait.
Oh,
can you go
sorry.
back real quick?
Yep.
Sorry, I'm just gonna
No, you're
stop
good.
here. Okay.
Okay. This is another fantastic problem. There's a couple different ways that you can go about executing this problem, but the setup is exactly the same. The only differences have to do with how we're going to type it into the calculator. Okay? Giovanni's grandmother wants to buy a savings bond for him to use when he goes to college in 18 years. So Giovanni is a baby. So here's our time. The savings bond has an interest rate of 6.92%. 6.92%. I can't leave things in percent form.
Times it. Subtract. Divide.
I'm going to need the percentage to cancel out. The way that works is by dividing it. Now, is this account going to be earning 6.92%? Losing 6.92%? It's growth. So I'm not just looking at this 6.92%, but it's going to be added on to the whole investment. So what do I have to add on to this?
What?
100% has to be added on to this. So we've got what's actually going on with this account is 106.92%. This is telling me my growth. That's this point, or this part. This is telling me my rate. It's in percent form, and I don't want to leave it in percent form because I can't use it like that in my equation. So I divide. We're going to divide this by 100%. That's going to make my percent part cancel out. And it means that I'm using what in my equation? 1.0692. This is our B value. If your B value is very large, like very large, it's probably incorrect.
If what's really large?
If your B value is very large, like if you have a number like 100 something or even 15 something, it's probably incorrect. Most of the time our B value, because growth usually doesn't explode. It takes a while to grow over time. Also, your B value will never be a negative number. It's not possible. All right, so we have our percent, we have our time. What else do we have to work with here? Is this how much she's putting in? That's how much she wants when? After 18 years. So this is the future amount. So when I'm thinking about the basic form of our exponential function, would I take that 30,000 and put it in for A? No. It can go in for Y. We already have a value for B. We already have a value for T. It's not the initial amount, so it can't go in for A. The only other spot is Y. So we have 30,000 equals A times, and now we've got this 1.0692 to the power of what? 18. All right. Here's where our plans, our paths might diverge. So here's how I would approach it. You're going to get a more precise answer this way. I would type this into my calculator, but then I would not round that value. And I'm going to take that number and divide both sides by that. You could even type it into your calculator the way I'm writing it. 30,000 on the top part of the fraction. On the bottom, 1.0692 to the power of 18. Pop it into your calculator, and you would be all done at that point. When I do it in its exact form and I don't round until the very end, I get that she needs to deposit $8,996.22. If it makes you uncomfortable typing it into your calculator, still with the exponent in it, and you're like, I'd rather just type this in and write it as a decimal. What do you get when you do 1.0692 to the power of 18? All right, so I heard 3.33, you said 4?
Yes.
If you divide both sides by 3.334, your answer will be a little bit different, but it should not be enormously different than the exact form. Go ahead and type this into your calculator and tell me what you get. Yes, you may.
I got 8998.
8998.
Yeah.
Point what?
20.
Point 20? I would accept that. I would accept that. Because in reality, if Giovanni's grandmother has this worked out for her, or she sits down and does it herself, and she comes up with this, is she going to deposit $8,996, or is she probably going to round that up? She's probably going to round it up to what? Probably 9,000. Like, thinking real life-wise, she's probably going to round it up to $9,000 if she goes through with this plan here. And so at that point, the difference between our 8,996 and the 8,998, not a huge difference. Most people, when they're making large investments like this, are going to round it to a whole dollar amount, like a nice, pretty dollar amount. I would accept either one of these as correct, or any value in between those two. Yes, ma'am. Number 2, absolutely. All right. The population of Cyanobacteria quadruples. What does quadruple mean?
4.
Multiply by 4. That means this is my base. 4 is our B value. This is an unusually high value for B. Quadrupling is a very, very, very fast growth rate. Does it do it every hour? No, it does it every 5 hours. If I wanted to know how much it had grown in 1 hour, what would I need to use for the exponent then? 1 out of 5. If I wanted to know how much it had grown in 2 hours, I would need to do 2 out of 5. So when you see every 5 hours, let's see, 1 hour would be 1/5 of the time. So my exponent is, I'm going to do number of hours divided by 5. Because that allows me to take any number of hours and pop it in. If it was happening every hour, I wouldn't need to divide. But because it's not happening every hour, if 1 hour is not the same as 1 quadrupling, then I'm going to need to have a fraction here. Does that make sense? A little bit? All right. How much are we starting with? 90 bacteria. So this is my A value. So for my rule, I would have y equals 90 times 4 to the power of h divided by 5. If you had that as 90 times 4 to the power of t, I would count that as correct. because T means time. You would have to be much more careful on part B, though. Because on part B, we're checking in on these guys again after how long? 40 hours. My exponent needs to tell me how many times they have been multiplied by 4. They're not getting multiplied by 4 every hour. So I'm going to put 40 in the place of hours here. And because it's not happening every hour, it's happening every 5 hours, I need to divide that by 5. What is 40 divided by 5? 8. So this is telling me right here that the bacteria have quadrupled eight times. I popped it into my calculator and I get an absolutely astoundingly large number. It's in the millions. Like I said, quadrupling is a very, very, very fast growth rate. That's like you start with 1, you come back in a little bit and there's 4, and then you come back and then there's 16. And then 64, and then it grows very, very, very fast. This is 5,898,240 cyanobacteria. I could be misspeaking about this, but I'm pretty sure I'm not. Have you guys ever heard of blue-green algae?
No.
I know what algae is.
Pretty sure that's what this is. And it is problematic. It is, like, it loves fertilizer. And you wouldn't think that that's a problem, except what happens to all of the rainwater as it runs off the farm fields? Goes into the rivers and the lakes. And it gets funneled down the rivers and ends up in our oceans, where these guys live. And they eat it up. And their populations explode, and they live on the surface of the water. Do you know what happens when they live on the surface of the water and their population explodes? They make it much darker for everything underneath. And the things that live underneath it that need sunlight, not as much as we need, but need sunlight to survive, all of a sudden there's this blanket over the surface that's blocking the sunlight, and it causes the things below it to die. So it's very happy about the fertilizer, but that's not a very good thing for the health overall of the oceans and the water. But this growth rate for cyanobacteria is not too far off of like realistic when you're looking at when it's been flooded with fertilizer. It just absolutely explodes, and this is why it's a problem. This is why we'll see like coral bleaching happen, because it blocks the sunlight from everything below it. Yes. Number 3, absolutely. Oh, this is another good opportunity to talk about a function rule. Yay! Is this showing us a linear function or an exponential function? Exponential. How do we know it's exponential? It's decaying. Linear things can decay. How is it decaying? What's happening each time?
It's decreasing.
It's decreasing. It's going down by the same amount. It's being cut in half each time. So each time there's only 50% left. If it was decreasing by 100 each time or decreasing by 10 each time, if you were subtracting the same number over and over, that would be linear. When you see it getting smaller because of division, that is exponential. Write a function rule that best fits the data. I can write this two possible, well, more than two, but I'm going to demonstrate two possible correct ways. A lot of times students will look at this number right here and they'll write their function rule based on this, and you can as long as you're careful. Is this the starting amount though? No. We got to go backwards. I can write a function rule from this, but I just have to know that that's not the very beginning. So I'm going to put a 1/2 here. You could put 0.50 if you wanted. My exponent is not going to be just x though. What was the x value up there? 3. So x minus 3. I can use that first value on the table, but I have to make a note that it is 3 into the future. So if I wanted to get back to the beginning, I'd have to subtract 3 off of it. Does that make sense? Yeah. Okay. The other way is to do what you suggested, Mia, which is the way I would recommend. We need to hop back to the beginning. So 3, I'm going to count backwards. 2, 1, 0. You got to go all the way back here to get to the y-intercept. What was happening each time as we moved forward on the table? It's being cut in half. So what happens as we go backwards? It's doubling if I go backwards. So 400, 800, 1,600. Yep. So you could write it with that initial amount, and then you don't have to worry about the part with the exponent. 1,600 times 0.5 to the power of x. Whenever you write a function rule, it has to have 2 unknown values. You have to have 2 variables, or else you didn't write a rule.
But what if it only has
If it only has one unknown thing, only has one variable, you're finding a specific point, one dot on that graph. If I want to know all the possible points for that graph, I need 2 variables there. All right, last part of this. Is this showing me growth or decay? Decay. How do you know?
Because it's decreasing.
It's decreasing over time. The y values get smaller as x gets bigger. Awesome. I showed you guys where the answers are. I showed you guys where my solutions key is with all my work. For anything where I had to write a story or anything where there's rounding, if we're off a little bit, that's okay. If you're concerned about it, contact me. I'll tell you whether or not it's enough to make a difference, okay? I will post this video today after school along with all the problems that we worked through together. And 7th period, I teach another section of prime. They often ask different questions, so I post both videos. That way you guys can see anything that I went over in that class that we didn't get to in our discussion in here. All right?
All right.